Perfect.
And in terms of time, like we are looking for what, 40 minutes? I forgot.
Yeah, we just have, you know, the usual hour slot. So up to you, like 40-minute plus
So
Q&A, 45 plus Q&A, or something like that, right?
So I'm aiming for like 40, 45. It shouldn't go more than 45.
Sure. And cool. And yeah, Milan, if you want to make me co-host or something, if the connection doesn't.
Sure. Yeah. So okay. I have to leave a little bit earlier. I have to go pick my daughter up, but yeah. Let me.
So what time is it now over there? Is it afternoon?
2:30.
2:30. Okay. Yeah. That makes sense. Yeah. Because it reminds me of
it's
me picking up my daughter. I have to pick mine too, and I'm like, oh wait, it's already. And then I'm like, oh no, it's not already there.
Maybe drop.
No, exactly.
All right.
Okay,
great. We're live. Thanks.
So we're live. We're recording. You know, I have the mic with the broadcaster audio, hopefully, or something like that. So I'm very, very happy to have you guys here for our privacy and security in ML seminar. So this week we have Suman Jana from Columbia University, and I am super biased on the topic that Suman is going to tell us about, but it's really exciting. I mean, I guess that, you know, even if you're not working in the field, really, it is so interesting and exciting to understand, you know, how the latest advances really in machine learning that stems very often from large language model and natural language processing are affecting also security and even tasks that you wouldn't think of, like in terms of trying to understand whether we can learn semantics of programs and whether we can transfer this learning to different downstream analysis and see whether this works. So I guess, you know, this will be what Suman is going to talk about to us exactly. And Suman is an associate professor in the Department of Computer Science and the Data Science Institute at Columbia University. His primary research interest is at the intersections of computer security and machine learning. And his research received 6 Best Paper Awards, a Communication of ACM Research Highlight, a Google Faculty Fellowship, a JP Morgan Chase Faculty Research Award, NSF Career Award, and an ARO Young Investigator Award. So without any further ado, I'm really pleased and thank you very much, Suman, for accepting our invitation. So now the virtual stage is all yours. Take it away. Thanks.
Thanks, Lorenzo. Thanks for the great introduction, and thanks, Emiliano, Lorenzo, and everyone else for inviting me to this talk and for attending this talk. So as Lorenzo said, we are going to talk. I'm going to talk about scalable, accurate, robust binary analysis with transfer learning, and the goal of this talk is essentially to show you that this latest advances, as Lorenzo mentioned, in NLP, domains like NLP, these large language models, when modified in a certain way, has a lot of promise, has shown a lot of promise in tasks that typically are done through heuristics in security. Right, so binary analysis is kind of one example of such tasks. This is joint work with my students, Keshin Pei, Jonas Guan, Zhao Xuan, and my colleagues here at Columbia, Bashakire, Junfeng. All right, and if you have any questions, please do ask. I'm happy to take the questions in the middle. All right, so, okay, sorry, let me just, one more thing. Let me just set up the laser pointer so that it's easier. Everybody can see my pointer?
Yes.
All right, yeah. Okay, so binary program analysis, as you probably know, consists of many fundamental tasks, and it's one of the core techniques for many security tasks like malware analysis or vulnerability detection or reverse engineering, patching or security retrofitting, or even forensics after certain attacks has happened. Because in most cases, when you're talking about security-related incidents, getting source code of the software is hard. So you only have access to the corresponding binary, and you have to perform these tasks on the binary itself without access to the source code. So this, as I mentioned, has many critical security and performance related applications. And binary analysis, again, just before we move forward, to provide a definition, is essentially the process of understanding, analyzing, and answering questions about program behavior best with only access to the binary, without any access to source code. For example, you can ask questions like, given two functions, the binary code of these two functions, are these functions similar? So that will be an example of a binary analysis task. And to understand why this might be difficult, imagine these two functions, even though they might have same source code, they might be compiled for two different platforms with different compilers and with different optimization level. So that might make the binaries look very different, even though they're performing the same operations, the same functionality. And then another example of a binary analysis task can be, given a memory location, can it overflow? And obviously, in this question here, I'm showing source code, right? I'm saying int I or char buff. But of course, in the binary, you don't have such information. You will just say, well, can this memory address, potentially overflow, right? So those kind of questions are essential for tasks like vulnerability detection. And then finally, you can also ask questions like, given two functions, does a function call the other function? And again, this kind of tasks, this kind of questions are related to the tasks where you are trying to recover, say, control flow graph from a binary. And again, control flow and data flow graph, recovering them from the binary, again, is a building block of pretty much any sort of reasoning tasks that you might want to do for malware analysis or reverse engineering. So these are very important core building blocks. And all of these tasks essentially require recovering some sort of program properties and dependencies across memory addresses, dependencies across registers, stuff like that. And again, just to give you some more concrete examples of binary analysis tasks, disassembly is one where you take in a raw binary, just the bytes, and then you produce the instructions, right? The instructions, the machine instructions corresponding to the binary. And then you might also want to detect the function boundaries in a binary, the function beginning and the function ending. Because remember, in the binary, this is a non-trivial task. And then you might also want to learn the data types, because obviously when you are writing source code, you specify the data types. But remember that information is stripped out during the compilation process. So once you have only access to the binary, recovering this information is hard. So, but that's part of this analysis. And then finally, as I mentioned, you might want to recover the control or data flow graph information, either complete or partial, because you want to use such information for further downstream analysis tasks, like malware analysis or reverse engineering or understanding program logic. So these are some of the examples of binary analysis. And then, of course, at this point, I guess I have already repeated a few times that binary analysis is fundamentally challenging. The main challenge comes from the fact that the high-level semantics that is present in the corresponding source code are absent in the binary because the compilation process and the stripping process removes those information. And again, if you're not familiar with the binary analysis process, if you're wondering, compilation, of course, I'm assuming everybody knows what it is, but the stripping process essentially makes the size of the binary smaller by stripping out all the debug information or certain hints about the source code that might have been present to make debugging easier. So that's the process of stripping, and in most binaries that are shipped for deployment, usually they are stripped again to cut down their size. So therefore, it's even harder to recover that information. And just to understand what this means more concretely, if you think about source level constructs that a programmer use to express this logic, right? For example, variables, arguments, types, data structures, names, stuff like that. All of them are removed essentially during the compilation process, and it's mapped into registers and memory access. So essentially, the binary analysis process will involve reverse engineering this mapping to some extent, depending on the task, right? How coarse-grained or how fine-grained the reverse engineering you want it to be depends on the task. So that's kind of the main challenge. And of course, this is further complicated by the factors that the process of compilation itself can have a lot of variance, right? Because there are many different compilers that's out there. So one might be picking any one of the compilers, for example, GCC or Visual C++, Microsoft compiler, or a bunch of other compilers too. And then you have different operating systems, the target operating system, and the operating system often have a native binary file format. So the syntax of the binary files are dependent on that too. And then you have different architectures that have different instruction sets. So therefore, the opcodes, therefore the binaries will look different in different architectures. And finally, you might have a different optimization level at the compiler, which tries to kind of cut down redundant code to make the code perform faster. But in that process, the output of the compilation might look very different, even if the input is same. And then finally, you might have some obfuscations. Malware often use some sort of obfuscation to make this binary analysis task harder so that the analysts don't get to see the real malicious behavior. And of course, just to be clear, dealing with obfuscation is a very hard problem. Here, the examples I'm going to show will deal with simple obfuscations. The hardest obfuscations are the one using cryptographic methods. They are very hard to deal with. So we're not going to go there. So these are the main challenges. As I mentioned, and existing solutions are heavily heuristic driven. And another problem with them is as the binary size grows, they tend to be quite slow and they're brittle. We'll see in a second what we mean by brittle. And machine learning, of course, we are not the first ones to use machine learning in this context. It has been used before, and it has shown promise. It's cheap because you have data. So it's a data-driven approach that saves the manual effort. And the neural network architecture, as we all know at this point, is designed specifically to exploit the parallelism offered by GPU, which makes them efficient. And in the typical setting in the prior work, essentially what you do is you set this task up as a supervised learning task. So you have a bunch of raw binaries, you have the labeled output, whatever you want the task to be. For example, in disassembly, the labeled output might be, which bytes are function boundaries, which bytes are not, where is the instruction boundary for each byte. That sort of stuff. And then you just train a neural network model. You have different architectures to pick from, and then you apply this on unseen binaries, right? So that's kind of fairly standard model. It has shown quite a bit of promise. But the main issue that we noticed was that the learned knowledge in this process is not retained across models, and also this way of training doesn't fully exploit the interdependencies between the tasks. A lot of the binary analysis tasks basically use similar common subroutines. So if you are training them separately, you have to learn those subroutines, or at least some implicit representation of those subroutines repeatedly, again and again, right? Which seems a bit wasteful. So that was kind of one of the main motivation for trying transfer learning in this context, and as this has been observed in vision or NLP domains as well. So our goal is to pre-train for learning general program behavior, right? So the idea is you have a bunch of raw binaries. You want to design a pre-training task that will teach the model, in this case, this large, you'll see in a second what kind of model we use, but it's going to be variant of BERT, this large language models essentially. And the goal is to teach the model the knowledge of program semantics, right? And once you have that, you can then fine-tune the model for specific tasks like disassembly, binary similarity, or any other binary analysis task. So that's kind of the paradigm that we are gonna operate in. And again, this is very similar to the standard transfer learning paradigm in other domains like NLP or vision. And the main advantage, again, as I mentioned, is to be able to exploit the interdependency between the tasks, and also better use the training data, because you don't need labeled training data for the pre-training process. You only need labeled training data for fine-tuning process, but the amount of data you'll need for fine-tuning is much smaller. And also, we hope that this particular approach will be generalizable, as it has been shown in other domains. You don't want to learn task-specific spurious features. You want to learn as much semantics as you can. That's the hope. So that's the basic idea. And in this talk, I'm going to talk about two projects. One is doing disassembly using this paradigm. This is called XDA. The other is Trex, which is going to extend this paradigm a bit. It's going to learn both on raw binaries as well as its execution traces. So that's a unique thing of programs, right? In natural languages, you don't have traces. You just have the language. You just have the text, sorry. So that's the unique aspect of code, or binary for that matter. And we're going to exploit that as part of the Trex design. So we're going to talk about both of them. First, we're going to talk about XDA. So the main goal of XDA is to build a disassembler, right? And as part of the disassembler, you want to do two things, two main tasks. One is recovering function boundaries. So remember, you are given a binary with raw bytes, right? You don't know where the functions start or where the instructions start. So these are the two main tasks. One is to identify where the function begins and where the function ends. And there can be many functions, obviously. And the second is recovering the instructions themselves, right? Where the instructions begin, where the instructions end. And you might be thinking, well, it's no big deal. I mean, what's the big deal? Why is it hard? Well, think of the Intel x86 architecture, right? It has variable length instructions, okay? And the instructions are very rich in the sense that if you feed spurious data that is not even code, it will still, there's a high likelihood that it will still decode to something valid, right? And compilers often mix code and data. So that's kind of one of the main challenge in this process, right? And I'll show you some examples. And again, this is not a new problem. As I mentioned, this is one of the core building blocks of pretty much any binary analysis task. And therefore, there have been many existing work and tools. There are a large set of popular non-ML based, more heuristic-driven reverse engineering tools. IDA, Ghidra, some of these names might be familiar to you, but there's a bunch of others too. And then there is ML-based approaches too, which try to solve these things mostly in the supervised learning setting. And they use different kind of models or different learning techniques. So that's kind of the main two lines of approach that has been done in the past. But of course, despite all this work, the existing tools suffer from fairly serious limitations, right? First, as I mentioned, the ability to distinguish between code and data is limited. And often compilers mix code and data while generating the code, right, from the source code. So here are two examples. So this is the Vim 8.2 compiled with Microsoft VC 2019. Let's take a look at the top example first, right here. So as you can see here, this is essentially a jump table. A jump table is essentially a table that contains the target of a bunch of jump instructions, right? So this is data, right? So you should not treat this as code. If you treat this as code, you're going to get a bunch of assembly instructions, but which are not valid, right? So here, objdump is an example of a disassembler. It's a very simple one. It's a linear disassembler. That means it takes a starting point as input, and then it keeps on disassembling from the top sequentially, right? So obviously, it cannot tell this existence of this jump table. It thinks of it as code. But the interesting point is the Intel architecture is so rich, right? The instruction set that it still decodes to a bunch of valid instructions, as you can see here. But obviously, even though they are syntactically valid, they're not right in the sense that these instructions will never get executed, right? The data, these are not even instructions to begin with, right? The source of this these things, right? So that's just one example. And then on that, so this will result in a false positive, right? Because you are kind of treating data as code, right? Which is not code. And then at the bottom here, if you can see my pointer, here's another example where you have a function start here. So this is the code generated by the compiler for the beginning of a function. And Ghidra, which is a state-of-the-art disassembler, I mean, it's a binary analysis platform. It has a disassembler inside it too. It treats this as data, okay? And this results in a false negative. So you might be wondering, why does Ghidra treat this as data, right? Because remember, the core problem is to separate code from data. So the approach Ghidra takes is it tries to figure out all the targets of the jump instructions, jump or call instructions, right? If it finds something that has that is not a jump target, right? There is no jump or call instructions that Ghidra can find that has a particular location as a target, it will treat that location as data. Because remember, you can only jump to the code, right? You don't want to jump to the data, I mean, by definition. The problem is because of the dynamic nature of code, right? Computing all the jump targets is an extremely hard task. So no matter what you do, it's most likely statically, right? You are going to be incomplete in the sense you're going to miss some parts. So this is one such example where, for whatever reason, Ghidra missed this particular function start. It didn't realize that somebody else is calling this function essentially. And then therefore it treats it as data. And therefore you get a false negative, right? So that's just another example. And then secondly, it's brittle and not very robust, right? So what do I mean by that? Well, remember, in order to detect these patterns in function prologues, right? So function prologues are the piece of code that the compiler generates before generating the actual code for function. Right? So it's supposed to do things like, save the register, clear up the stack so that there is enough space for local variables, stuff like that, right? So this usually follows a simple pattern. So there are rules in this disassemblers to detect these things, right? So that's good. But the problem is once you increase the optimization level, these patterns becomes much more, how should I put it, diverse, right? In a sense, the simple pattern of like a bunch of like push instructions, for example, here becomes much more compressed. So these kind of patterns are much harder to detect. So that's why the simple heuristics that a lot of these tools, existing tools are using, struggle to detect such cases. And another thing to notice is that recent work have shown that a lot of the past work on ML approaches for this sort of task had huge training and testing set overlap. So the numbers that they got, the accuracy numbers, are higher than what they should be, right? In real life, because in real life you want to test it with as little training and testing set overlap as possible. So that's one of the things to remember, that the numbers, even though the reported numbers might be high, the brittleness, is still there. Part of it was bypassed because, unintentionally the training and testing set had larger overlaps, right, in prior work. And then finally, maintaining these heuristics, these rules for detecting these things require a lot of human effort. For example, IDEA has around 41 megabyte of patterns database, right? And Ghidra has even larger, 180 megabyte of pattern database, right? And remember, the reason they're so large is because they have to support all sorts of different compilers, different hardware platforms, different instructions. And as I said, these patterns keep on changing, right? Even a substantial patch to a compiler might break some of these patterns, right? Because the compilers have to keep on getting updated periodically. So these are kind of the main limitations of the existing tools. And in terms of XDA, let me provide a quick summary first before delving into the design. So the goal, XDA will use this transfer learning paradigm. And as part of XDA, as I mentioned, the goal is to be as accurate as possible. And it achieves very high F1 in both of these tasks, as you can see here. And it outperforms the state of the art by a fairly large margin. As you can see here, it's 17.2. And it's robust in the sense that we have specifically tested across different compilers, different operating systems, different optimizations, obfuscations, all sorts of variants that the prior literature has mentioned. And we also have ensured that the training and testing overlap is minimal. And of course, the other feature that is kind of we almost get for free by design is that it's a sorry, I apologize for the noise. It's the semi-supervised learning setting, so you don't need labeled data. But that's just the benefit of the transfer learning paradigm itself. Right. So remember the task we are interested in is recovering function boundaries and recovering assembly instructions. So the insight, as I mentioned, is using the transfer learning paradigm. So we're going to pre-train the model to understand machine code semantics from raw bytes, and then we're going to transfer. So that's the key idea. And here, for example, is a sequence of bytes from a binary. And what we are going to do as part of the pre-training task is, again, very similar to what they do is in this large language models. We're going to use a mask language modeling task as pre-training. So we are essentially going to mask certain bytes in these binaries. We'll collect a large set of binaries. We'll mask certain bytes and force the model to predict these masked out bytes based on the context, based on the surrounding bytes. Right? And the idea is that this sort of prediction will help the model learn, implicitly learn the semantics, at least up to some extent, of this binary instructions. So that's the goal. And then finally, once this pre-training is done, we're going to fine tune for this specific task with a little bit of labeled training data. Right, and we're going to predict the function start, we're going to predict the function end, as well as the instruction beginning and end. So again, just to give you a bit more intuition here, why this kind of masking can help, consider this byte stream that have been taken from the .text segment, that's the code segment of a binary. And this is the corresponding disassembly. This is the corresponding instructions. And as part of pre-training, remember, we are masking random bytes, right? And we are training the model to predict the masked part based on the context, right? So this is, for example, is a function prologue, right? And as I mentioned, before the compiler calls the actual function, generates the code for the actual function, it will, set up the calling mechanism. So to save the registers, it will clear up enough space in the stack for local variables, stuff like that. So this is what this code is doing, right? So if you, for example, block this byte, right, mask this byte, let's say 0x28, it's essentially blocking, masking how much the stack variable has to shift, like basically how much space to allocate for the local variables, right? Now, if it is to recover this value based on the context, again, implicitly, it has to understand some aspect of the local variable allocation semantics, right? So that's kind of an example to show how this kind of masking can help. And again, here's another example. This is a jump table at the bottom. And if I mask some parts of the address, right, it has to reconstruct the address, it has to somehow understand that this is a jump table. And again, all this is implicit. So obviously, you don't understand the full thing of the jump table, but it has to understand that this code is not reachable because there's a ret here, right? So this sort of stuff. Again, this is all implicit. We are only going to evaluate this through how well it works in the fine-tuning task, right? And we have also done some probing tasks to see whether this such a prediction works well for unseen code too. And it tends to achieve very high accuracy there too, right? So that gives us at least a bit of confidence that it's at least learning some aspect of these things implicitly. So that's the basic idea behind this process, and all this information, of course, is useful to infer the tasks that we are talking about, function boundaries or instruction boundaries. And the architecture, again, as I mentioned, is motivated by BART. Essentially, we're going to use this self-attention layers across this each token. So we're going to convert the binary file into a bunch of tokens, which is each bytes. And then each token will have attention connection to all others. And we are going to train this whole model through masking the bytes and then making it predict the masked byte. So this is the classic masked language model setting. It's just that we are changing the input from regular languages to this binary byte streams. And then we're going to fine tune the pre-trained model, again, with a little bit of labeled data, doing the transfer. So that's, in this case, remember, we are trying to do disassembly, right? So the goal is to predict these boundaries of instructions and functions. Right. So in terms of experiment, we use 3 different data sets, SPEC 2017, SPEC 2006, and BAP. They have a large number of binaries in them, as you can see here. They cover different platforms, Linux, Windows. They also cover different compilers like GCC, Microsoft VC, and the Intel's compiler. And then, as you can see here, the number of bytes are fairly large in these binaries. And they also cover both x64 and x86 architectures. And then finally, we specifically ensured that the training and testing overlap is small. And this, we use the methods introduced in prior work to measure this overlap, to ensure that, this overlap is minimal. And in terms of baselines, we tried both, ML-based and non-ML-based baselines. So we tried the state-of-the-art in terms of ML performance for this task. This is a bi-RNN-based approach. And then there's non-ML-based techniques like nucleus in the research literature. And also we tried, standard off-the-shelf reverse engineering tools. And these are commercial tools like IDEA or Ghidra, I guess, is open source, but IDEA is a commercial tool. And for recovering assembly instructions, we used some other specialized disassembler together with IDA and Ghidra. In terms of measuring matrix, we use precision, recall, and F1, all of these numbers. And this makes sense in our context more than accuracy because the labels are very lopsided, as you can imagine, right? Because functions are relatively rare, right? So the bytes that are function beginning or function end are far rarer than the ones that are not. So it's a little biased, the data set. Therefore, we use this matrix rather than accuracy. Again, this is fairly standard in machine learning literature. So in terms of performance, across all the operating system architecture and compiler and optimizations, the numbers are quite promising. It looks very robust, as you can see here. XDA is the top one on the red bar, and the others for function boundary detection there's a fairly large gap. In the assembly instruction, as you can see, the gap is a little smaller, but it's still pretty good. The interesting thing is OBJ dump, which is the simplest linear disassembler, is actually closest, right? 99.6. So we looked into this because this was a little surprising because OBJ dump is essentially the simplest disassembler possible, right? You give it a starting location, it just goes sequentially. That's it. It doesn't even try to distinguish between code and data. Right. So then we realized what was happening is that in our data set, the number of cases, the number of binaries that had code and data overlap was actually very small. So those are the ones where OBJ dump completely failed, right? But because the percentage was small, the accuracy was still pretty high. The F1 was actually quite high. So that's kind of the main thing. Essentially, OBJ dump made this design choice that they're not going to even handle that. But because that is a small case in our data set, the numbers look good. On the other hand, Ghidra, IDA, they try to detect those cases. But in the process, they introduce some false negatives and the numbers, get hard. That's kind of the basic finding from these numbers. And then we also checked for robustness across optimizations, different compiler optimizations between XDA and this bi-RNN-based approach, which was the ML-based approach, state of the art prior to our work. And as you can see, the interesting thing here is that because of the pre-training, XDA right from the beginning, like within a very few epochs, get very high accuracy here, right? This is the training epochs here, and this is the test F1 score here, right? So essentially, if we stop the training, let's say at 5 epoch, take the model, and then use that model for testing, right? We still get very high F1 here, right, for XDA. On the other hand, the bi-RNN based technique, takes quite a few epochs to get up, and even then, it doesn't quite reach there, right? There's a large gap here, and it fluctuates quite a bit, across optimizations. And it's not surprising because it doesn't have pre-training, it doesn't have this benefit of inherent, representations of some of the semantics. It has to learn it from the beginning, and it's not quite as good. So that's again one of the main findings of this. And then finally, in terms of the runtime speed, again, remember, because XDA is exploiting GPU, IDA and GIDRA by design cannot. So they're not, parallelizing them is much harder. So it's not a surprise that we get a large performance boost, as you can see here. And the bar charts for these things are sorted based on the size of the binary, right? So this thing's 0.5 megabytes, 4.1 megabytes. They're the size of the binary. As you can see, as the size of the binary increases, obviously the time taken to disassembly will increase for all the programs, right? But the rate of increase is still much smaller for XDA, partly because of the GPU parallelization, right? We also measured with CPU too. It still get a pretty significant improvement, but with GPU, the numbers are far better. It gets up to 38x speed up. And again, as you can imagine, it's not surprising that using GPU, you are going to get this benefit. But I think the important point is that you're getting all the robustness and all the other aspects together with this performance. So that I think is the interesting point here. Right. So in terms of summary of XDA, the whole idea was to use machine learning approach, the transfer learning approach, to try to teach the model the semantics of machine code. And this forces the model to learn robust features. This is cheap, and the results demonstrate that it outperforms the existing approaches by a large margin. And the code and data set are available open source if you want to play with it. So you can take any quick questions if you have about XDA. Otherwise, I'll move on to Trex. All right, so then I'll move on to Trex for the interest of time. All right, so Trex is going to take a different task. So essentially, we are trying to detect binary code that's similar. Okay, so limitations of the existing approaches. There are basically two classes of approaches: static and dynamic. The main issue, as you, I'm sure all of you know, is there is high false positive and false negative, depending on which side you bias, static or dynamic. And then you have the coverage issues in the dynamic approaches. And you have large runtime overhead if you're going to do multiple dynamic executions. And it will require non-trivial manual effort. And again, ML-based approaches are efficient because they cut down on the manual effort, obviously. And the main limitation is that the existing ML-based approaches rely only on static code, right? So there's no dynamic code here. And no dynamic understanding of the code, sorry. And this is tricky because, imagine looking at these two set of instructions, right? So on the left, they're doing the same thing, by the way, right? But they look very different, right? So that's the main issue, right? How do you teach the model the idea that each instruction has a side effect? And even though they look very different, they're same, right? So before I move further, let me ask Lorenzo or Emiliano, how are you doing on time?
We do have 15 minutes
okay.
to the 30 minutes mark.
Okay. So yes, I think I will probably go over some of these parts a little quicker than usual, but that's fine. All right. So again, in case you are wondering like how different the instructions may look, right, when you are taking the same source code and compiling it for different compiler architectures or different with different compilers, right? So here's an example for x86 and ARM, right? This is the same code. They are supposed to do the same thing, but again, they look very different, right? So in this case, they're comparing the lower 12-bit to 0x80. And again, I'm not going to go over the specific details for the interest of time, but the point is, even across compilation optimization levels, across simple obfuscation, essentially you can have a lot of code fragments that look very different, but essentially doing the same thing. And you have to somehow deal with them, somehow detect them, right? If you want to achieve high F1 for this task, for similarity detection, right? So that's kind of the main idea. And we take, again, a pre-training based approach to this problem. But the newness over XDA is that here we introduce the notion of values as well. So we're going to execute these binaries, right? These functions. We're going to micro-execute them. That means because you don't have the full code, you will take a function, let's say, you will jump at the beginning of the function, and then you will keep on executing. And if you find something where it crashes, you will try to fit a random value in there and then kind of still continue, right? So it introduced some noise in the process, but as we'll see, it will still very useful, right? And then we're going to pre-train both on this instruction and the value, right, together. And then we're going to transfer this knowledge to match binaries. Essentially, we're going to use the embedding learned during the pre-training process, and then going to compute the cosine similarity between the embeddings of given different binary inputs, right? And then if they're similar, the cosine similarity is gonna indicate that how close they are. So that's the basic idea. And in terms of architecture, remember here, we just don't have instruction. We have both instruction and trace value pair, right? So we are going to break them up into a different set of tokens. So you have the instruction, we have the trace value sequence, we have the instruction position, we have the opcode operand position, and the architecture. Because we're going to train for different architectures together. So we're going to basically support the different binaries for different architecture at the same time. So we need some markers, right, to say this is for x86, this is for something else, right? So we're going to put all of these tokens together. We're going to add them up, and then we're going to send them through these self-attention layers, right? And then we're going to mask randomly some part of the instruction and predict that. And also we're going to mask some part of the value, because remember, this is new, right? Because the value part was not there in the last case, or it's usually not there in the traditional NLP or vision and all the other domains, because they don't have such a concept, all right? So that's that. And in case you're wondering how this helps, so imagine this case, right? So there is a value here for ECX. If ECX is executed, like if this is masked, you have to predict, the model has to predict the value of ECX. And this means that it has to potentially reason about this, right? So the value was 2, you do a subtraction, what value do you get? So it has to understand the semantics of subtraction. So on and so forth. I'm not going to give all the examples here, but essentially it's learning, it's being forced to do different kind of reasoning that has been shown in the prior literature to be very useful to mimic human understanding. So this is not specific to code, this is in general. It's just that this kind of reasoning is being forced implicitly by the design of this task. And yeah, and that's like, sorry, let me kind of summarize Trex, and I think I will not go over the detailed results too much. But essentially, Trex is very accurate. It outperforms the state of the art in matching functions. It works very well across different instruction architecture. It gave, as you can see, 7.8% gain in F1 across different compiler optimizations and across different obfuscations too. But just to be clear, when I say obfuscation, we are trying very simple obfuscation. So we're talking about, inserting, let's say, some junk control flow instructions, right? Changing the control flow a little bit, or maybe adding spurious instructions that have no effect, no side effect. Like imagine adding a bunch of knobs, right? I mean, of course, knobs are the simplest, but you can do a little fancier stuff too. But again, nothing cryptographic in this sense. We are not there yet. That's a much harder task. So that's essentially, Trex. So again, I mean, if you have any questions, I guess I can take some more questions now, or maybe I can go to the end and then take questions. I don't know, whatever way you want to do it. Because I mean, it mostly, Lorenzo, it mostly covers whatever I wanted to cover. So there is some more performance number I can show or skip.
Yeah, so as you, I mean, you can if you want, you can just wrap it up with the performance, or the if you want, or if you want just to to finish here, then we can open the floor for questions. So
I think let's stop here, because if there are some questions more about performance numbers, I'm happy to show those, those numbers if it comes up.
Right. That sounds absolutely perfect. And let me just first stop the